Hello and welcome to the Embedded C Programming Design Patterns course. This course is available here on YouTube, and also if you don't want to wait until the next module comes out, you can get this course as a book, as book plus videos, Udemy course, and also all of the book and video content, as well as live sessions with me on Wednesdays, which is available at swedishembedded.com. So the book is available on Kindle. You can download it from Amazon. The Udemy course contains the book materials as resources, as PDFs here. And on the website, we have the course available as a standalone course directly on the website. You just click join here, enter your details, register as a student, and then you will have access to all the course materials and also the weekly Q&A, which is in 5 days, 8 hours at the time when I'm recording this. All right, so let's get on with the next module of this course. Hello and welcome to this training on design patterns in C programming. In this module, we're going to cover the Singleton pattern. The Singleton pattern basically ensures that there's only one instance of the object that you're creating. And we use Singleton pattern in places where we know for sure that there will always be only one instance. This is also a much misused pattern in C, unfortunately, because a lot of C code is written with global static or even global variables, which make them work kind of like a singleton. So we will look in this module how you can design good code and when you should use the singleton pattern and when you shouldn't use this pattern. There are three defining factors for the Singleton pattern. Number one is that you have control over the instantiation and use of this object. So Singleton pattern typically creates an instance in private inside the C module and then allows other systems to share that instance. And when we're programming in C, we are basically creating a static variable inside the C file, and then we're exposing the functionalities related to that object, either through an API that doesn't take the context as the first pointer, as the self pointer, or an API that does take the context, but then we make sure that we have tight control over who gets to retrieve the instance at any given time. And singletons also often have a stateless interface, and this means that the order of the functions that are being called should not matter. And this is an important feature of the pattern, because if you implement an API where the order of the functions matters, you will get you can very easily get into race conditions between different places in the application that try to use the same global APIs in random ways and potentially unpredictable ways. So one of the key factors in the Singleton pattern is that we're trying to make this API as stateless as possible, especially if you're not passing the context or the state of the object as the first parameter to the Singleton member functions. The member functions basically that are part of the object implementation. There are four basic use cases for the Singleton pattern. There's, of course, more use cases that you'll run into, but the four most common use cases is, for example, logging. Even when you start C programming, the first thing you do is you print to the console. And that is, the print function acts like an interface to the single console that your application has access to, which is output to the std out. And when you're creating embedded applications, such as if you're using Zephyr, for example, you have access to the logging module. And each one of your subsystems in your application can have its own private logging module that you can share across a number of subsystems, but it's still a global object. And so all of the logging macros provide you an interface to access this Singleton object that can be shared between a number of smaller modules or can be global for the whole application. Another example is configuration management. And in Zephyr, we have the settings subsystem that provides us with a very nice interface for storing settings. And It also provides the storage capabilities so that we can write settings to Flash or to EEPROM or to other storage media and do so efficiently. But all of that functionality is completely hidden from the user, and the user gets a very nice interface with the string keys to access different settings. And many subsystems follow this pattern. Many subsystems that are shared across the whole application and across all of the device drivers follow the simple concept of the singleton pattern. Another example is network management, where you have different network drivers that register with the network management stack, and all of the other application components that need to talk to the network. They use the global public interface of this network management API to interact with the networking stack. And that is a typical example of a singleton, where you have a single hub for all of the networking protocols that are supported by the system. You allow those protocols to register callbacks with this single hub, and you allow the other modules or applications interact with this single hub and make use of the systems that have registered with it, but without knowing the particular implementation of those systems. So you can have a networking protocol driver that implements Ethernet, and you can have applications that send IP packets, and the networking stack will transparently create an Ethernet packet and then send it over through the correct Ethernet interface. And singleton pattern is used to create those kinds of simplifications. Another example is the thread scheduler, where you create threads, and the scheduler then manages resource access for these threads, and when they should run, when they should sleep, when they should wait for some event to happen. And the scheduler itself is also an example of the singleton pattern. So what are some of the benefits of using the singleton pattern? Well, number one, and the most important, is of course that it ensures that there's only a single instance. And this is the driving force behind determining whether you need to use a singleton or not. Number two is that it simplifies the code, and primarily because you don't need to pass the context along the call path. You can just implement your functions using a global interface that internally keeps track of the context, at the expense, of course, that you can only have one instance. It does improve performance because we manage everything in one place, and we avoid passing data around. We can just have a single place, single hub that takes care of the resources that we're managing. And also, the singleton often provides this means of having a hub, kind of like a single place where you manage different resources and access to those resources. So just like when we have, for example, the logging subsystem that manages different types of log outputs. You can have a log output to the console. You can have a custom log output that sends your log over the network. You can have additional custom log outputs. And yet the application accesses this log using the same API every single time. So when we change the implementation a little, and let's say we add new functionality or we add new logging interfaces, we don't need to change the source code of the application. It still remains the same. There is just a single API that doesn't require any context to be passed around, and so the code can remain the same, and that simplifies the maintenance of the code in such cases. And there is, of course, reasons to avoid the singleton. And the primary reason is the mirror reflection of the primary reason to use a singleton. Whenever you have any chance at all that you will need to have multiple instances of a particular object, you should just directly avoid the singleton pattern, because you should only use it when there is absolutely no chance that you will need more instances later, because refactoring your code to accommodate for additional instances would require large changes in many different places in your code. So just the fact that you would need to add the state, the context variable, the self pointer to every single API call would require you to make large changes to your source code and pass this context to the relevant places to make sure that you have a full control over the ownership of that pointer. And so you don't want to do that after the fact. If you want to kind of avoid that and use an object pattern instead. So you wouldn't use a singleton pattern for UART drivers. You wouldn't use it for any other kind of drivers that where you can have multiple devices of the same type. You wouldn't use it for network protocols because you can have multiple implementations of network protocols. And network protocols can also be used on different network interfaces. So you potentially have a possibility that you will need to have multiple instances of that state. Whenever you're using abstract interfaces, the correct pattern there is to use the object pattern, where you implement the abstract interface as part of the object. Also in situations where you have things that need to happen concurrently, so that you need to have two different versions of the same state. So let's say you're processing a buffer, and you want to process two different buffers concurrently, depending on when the data arrives on two different interfaces. So the buffer object cannot be a global singleton. It needs to be an instantiatable object that you can instantiate twice and then use to parse the two different states. So it's kind of clear. Just make sure that if there is any chance at all that there is multiple instances required, then just don't use the singleton pattern. All right, now let's look at the implementation of the singleton pattern. So normally when you're writing C code, you would be using the object pattern. So you would always have an object and an instance of that object, and then you would have methods that operate on that instance, which you're passing here. So this makes it very clear that you're operating, you have a method that is part of the object class, and you're operating on an instance of the object itself. And when we have a singleton, we instead use a static variable, which is declared inside the C file, inside the implementation of the singleton. And we then operate on this static variable. So this is an equivalent of a static method in C++, but in C, the meaning of the word static is slightly different. So if we were to declare this static here, we would have a local method that is only visible inside the C file. So in C, static is a keyword that defines visibility of the function, while in C++, static defines that the function is operating on all instances of that object. And in this case, we have, if we declare this function like this without taking the self pointer, it effectively has the meaning that this function operates on the global instance of this object, or just on all instances, regardless of, there is no particular instance that it operates on, basically. So if we were to implement this singleton pattern in C++, we would have a static singleton pointer, and we would have another function that is called getSingleton, and this function would actually also be static here. So we would call this function as part of this class, and it would check whether the singleton has been initialized or not, and then it would allocate and initialize the singleton and return the singleton to us. In C++, we don't have this, we don't have classes, so we use structs instead. And also in C++, we would be able to use a singleton that is an actual instance which gets constructed during the startup of the program, but we still don't have a way to control when exactly it is initialized. So in C, we can have this control, but we do need some extra infrastructure, and Zephyr provides this infrastructure. So Zephyr provides the sysinit function. What this function does is it will place your init function here, which you pass as the first parameter, which is a static function here. It will place it into a special section in the executable file, and it will place it at a particular place so that the sections are sorted. And the second parameter here shows the stage at which it's going to be initialized. So there is pre-kernel 1, pre-kernel 2, and then there's application, which is the last the last stage of the initialization process. And we also have a fine-grained control over exactly when it gets initialized as part of this stage. So priority is a number between 0 and 99, which gets appended to the specific name of that section that's going to contain this function. And then when the executable is created, the sections are basically sorted, and the functions with the lower priority number will be run first. So Zephyr is responsible, as part of the init code, which runs before main. It's responsible for going through all the functions that have been placed into those special sections and calling them. So in C, we can implement the singleton like this. We can have an initialization function. We can then initialize the singleton, and everything is thread safe and nice. The problem with this C++ approach, and on-demand initialization in particular, is that we don't know exactly what thread is going to query the singleton the first time, and there could potentially be two threads that actually do that, and first check for the singleton here, and then get interrupted, and then end up creating the singleton twice. So this approach is not thread safe, and this approach is very simple and also thread safe. However, if so, by the way, here we can define a macro that will help us define new singleton types. So we want to define a function get singleton, and in C we can create a macro like this, define singleton type. And it's going to create the instance. It's going to define all the variables for us, basically, based on this type. So this is like a template, but in C. And we can ensure that if we are using the on-demand creation, the on-demand get singleton function that will create the object on demand, we can ensure that it's fully thread safe by using a spin lock in this case. A spin lock is only available to you if you are working on the RTOS level. If you're writing an operating system style application, you can use a mutex. But the spin lock is very lightweight, and it scales across multiple CPUs. And what it does basically is it disables the interrupts. So when the interrupts are disabled, you cannot have a context switch happen in between there. And it also stores the previous state of the interrupts into the key variable. And this pattern, with using a key variable here, it ensures that the spin lock can be recursive. So you can have another call to spin lock, and because the interrupts are already disabled, it's going to return the state that says that the interrupts have been disabled. So when the code then calls unlock, it's going to pass the previous state, and the interrupts will still remain disabled. And then the last call to this will actually pass the state from where the interrupts have been enabled, and they will be re-enabled again. So this section here, we call this a critical section. It's going to run basically in one sequence. It's not going to be interrupted by anything, not even the hardware interrupts for peripherals. So this ensures that we only create one singleton, and then we basically call the init function of the object, and the rest of it is kind of like the object pattern, basically. So in this case, we are actually returning the instance of this object, and we can then pass this instance around. So if you could obviously combine this with the previous pattern here, so you can have a get singleton that just returns this instance, and that's totally fine. This is just an example to show you how you can potentially implement it if you want to have this on-demand creation and make sure that it's safe, that it won't create any undefined results, because that's the worst thing in C programming, where you have something happening and you don't know why it's happening. And this is the kind of situation that creates that type of behavior. So there's a few considerations you need to keep in mind with the singleton pattern. And the most important is the self pointer. So the self pointer, you need to see it as a cue to how the state is being passed around. Whenever you see a self pointer, it means that whoever is calling the function essentially owns that state during that call. So it's not necessarily that the caller is responsible for freeing that state, but the caller has ownership of that state during the call. So this is a very powerful way of structuring your software, because you can pass your state around, and whenever you are passing it around, you know that whoever has that pointer at that time is also the owner of that pointer at that time. You don't get that if you have global variables, where everybody is free to access the pointer at any given time. But if you use the self pointer, you get very nice architecture. If you have a singleton, which basically with the instance defined in the C file, and you don't pass this self pointer, then that is also an indication. And you need to structure your code this way. You need to be actively promoting this ideal that when you're not passing a self pointer, it's an indication that you're working on global state. And then other considerations apply. So if you're working on global state, then your API should be very stateless, because you can have multiple parts of your application calling into this API, and you don't want there to be any race conditions or side effects between the calls. So you don't want to have, for example, if your API involves locking, like you can see here, if your API involves locking and then doing something and then unlocking the singleton, this will not work. This will be a race condition. So you will have one code called lock, and then expecting that these functions, that nothing else will call or modify the singleton object in between here, but that's not the case. And you don't have a way of ensuring that nobody else can can do anything with this object in between. So for this, we need a separate way of implementing the singleton. But generally, you should avoid this type of API, and just do the locking inside the functions themselves, so that each operation is atomic and very self-contained. So if you do want to implement the singleton with management of the ownership of the pointer at any given time, you can do it like this. So you can have an acquire and release function. So this is equivalent to this lock and unlock, but we call it acquire and release just to be a little bit more clear that what this implementation does. And this acquire a singleton and release singleton is going to basically just mark the object as being in use, and will then return this object that is currently being in use. And if somebody else tries to acquire the object at the same time, they will get a 0, basically a null return value to indicate that the object is being used. And you can see how this already starts to break down. This is not a good architecture to have in your application. You shouldn't have stateful APIs in this way. So you're gonna always have to check the return value, but this is a workable way of doing it. So just to ensure that there's only one owner. So this is a possible implementation, but it's not a clean implementation. There's better ways to structure your code to avoid even having to implement this. So basically, you would acquire the singleton, you would do something to it, you would release it. And now this is guaranteed to be atomic, because anybody who tries to acquire it, they're not going to get the right pointer. So the application will either crash, or if they handle the return value properly, they will be basically just getting an error. So what are the best practices then of implementing the singleton pattern, and how should you do it? So try to apply the automatic initialization. You want to have full control over the initialization. So you want to initialize it before you get to your main application and before all of your threads starts. So use automatic initialization, and also do it as early as possible. So try not to do a lot of complex work in the initialization, but if you absolutely have to, you can set the initialization priority to application, for example. Let's say you need to use some driver access in your initialization, then you cannot initialize before the drivers have been initialized. You have to do it afterwards. So then adjust the priority and do it a little bit later, but still before the application starts. Have the stateless public API. Avoid singletons as much as possible. So generally, you should avoid singletons. Like there is very few places where they are a good choice, and those places are very specific. It's obvious that there is only one instance of that particular object. One of them is scheduler. So you wouldn't have two schedulers. You just have one scheduler that manages resources, manages multiple CPUs and multiple threads and multiple processes potentially, but it's still only one scheduler. And if you're using on-demand instantiation, just to be safe, you can use the lock. On RTOS systems where you just have one CPU and things are very simple, it's not strictly necessary, because most of the time you won't run into problems with that, especially if you have a very predictable way of switching tasks, where you can ensure that the task actually gets to run, so based on priorities and based on the scheduling algorithm that you're using. But there's still something to keep in mind, that you might need to use the lock. And try to hide the instance. So if at all possible, try to adhere to the pattern that if you're passing a self pointer, the caller owns that pointer at that time. If you're not passing a self pointer, it means that you're calling into a global, you're modifying global state. And if you're passing a self pointer, make sure you don't modify any global state. That's also a very important point, and that's part of the object pattern implementation and rules for applying the object pattern. Some of the common pitfalls of using the singleton pattern is, the most common pitfall at all is overusing it, because you'll see this pattern abused in almost all of the C code that you'll come across. Because in most C code, programmers define static global variables and sometimes even define static variables inside functions, which is like a big no-no. But that's what happens because the C language doesn't enforce any particular pattern of coding in C language. So we have to create our own patterns that help us create better software. But what you'll see is that this pattern is basically abused in many places. And if you have that kind of implementation that doesn't consider that uses the pattern even though it's not the right choice, you will have problems such as if you want to add another instance of that object, or if you want to have control over the data flow. Like the major problem with global objects is that you don't have control over the data flow. So it's not clear how the data is moving around and who owns the data when. And you will have to do a lot of refactoring to fix those problems. You would have to first start by implementing the object pattern for most of your code that maybe originally uses singletons, and then to implement singleton pattern only for the places where it actually makes sense, right? And where it makes sense is basically services, subsystems, like larger hubs that organize resource access, and objects such as scheduler that is also basically a hub that manages the resources from many different places. And everything else should be using the object pattern. And the last pitfall is cutting corners. So thinking that, well, now we only need one instance, maybe later we can shift to using more instances. And then you basically do what is lazy, not passing the self pointer, and you end up with a singleton where it's not warranted that you should be using singleton. So if there's any possibility at all that you will have multiple instances later, or you want to have full control over the data flow, you should never be using singleton. The main alternative to the singleton pattern is the object pattern. And in fact, when you start using the object pattern, you will try to convert all of your code to use the object pattern. In most cases, it makes sense. And the only places where it doesn't make sense is where you need to access the global state from many different places. One example is the logging function. You need to log messages from many different objects, many different places in your application, and you don't want to pass the logger around into all of these places just to call the log function. So that's a guideline for using a singleton in that sense. Like if you have a logger, you would typically implement it as a singleton. But if you have, for example, network connections to different clients, that would be a typical object pattern. And for most other things, even the application itself, just structuring things as an object pattern is a much better choice. The factory pattern. The factory pattern is similar to the singleton pattern in the sense that the factory can be a singleton if it's also managing the resources. So the factory pattern can actually also apply the singleton pattern itself, unless you have the abstract factory where you have different implementations of the factory. The prototype pattern, where you copy an object. So you're taking one object and you have a virtual copy method that is able to give you a copy of that object without knowing the particular implementation of that object. So that's a variation of the factory pattern. It's just that you're using a prototype to create a new object. And that is also highly related to the object pattern as well. So the object pattern is kind of the main alternative to using a singleton. And also another alternative is the endpoint API pattern. And this is kind of like a, you have a global API to make calls to other subsystems, but the calls themselves are hidden behind things like IDs or paths. So one example is that, for example, if you have a path that, let's say you want to write to a file, which would be a path, and you call a function to open that file, and you supply the path, and then you write to that file, and all the details of writing to that file are hidden behind this single interface. And that's called the endpoint API pattern, or also service locator pattern, where you have different services, or in this case, like different files, that are accessible through this single interface. And then you can interact with those services. And the service, each service itself would implement the object pattern and then register with this service API gateway, if you will. To expose it to the rest of the application. But what it all comes down to is basically the main alternative is still the object pattern, and making sure that the data flows with the code and not outside of the code. So we have covered the benefits and drawbacks of the singleton pattern. We have covered, we have looked at code examples of how it's typically implemented, including some of the less known code examples. We have looked at potential problems, and we have looked at alternatives and when and why you should be using this pattern. So to verify your knowledge of the singleton pattern, you can go through this quiz. What is the main purpose of this pattern? When should you avoid using the singleton pattern? How is the singleton pattern implemented in C, and how is it different from C++? Give a few examples of common use and use cases for the singleton pattern in firmware development. So this would include the logging system and other types of subsystems that are part of the firmware. What are the best practices when implementing this pattern? What are some of the common pitfalls? Can you see some cases in your existing code where you should use the singleton? And can you also see some counterexamples where you should actually be using the object pattern, where you might be using singleton pattern right now, but where converting the code to use the object pattern would be a better approach? So that's it for this video. Thank you for attending this lesson, and I'll see you in the next lesson.